Okay, so thanks for coming. So today I'm going to be talking about kind of the past, present, and future of polarization observations of protoplanetary disks, specifically at millimeter and submillimeter wavelengths, and what those observations can tell us about the properties of dust grains in disks, and why you should care. Okay, so I know a lot of people in this room are familiar with protoplanetary disk evolution, but just for some context, a lot of the sources that I'm going to be talking about fall kind of into this zone in this cartoon of disk evolution going from a cloud of gas and dust to a full-fledged planetary system. So in most of the sources that I'm going to be talking about, most of the envelope has dissipated, but the protostar is still surrounded by a disk of gas and dust. So when we look at protoplanetary disks at very high resolution, at millimeter and submillimeter wavelengths, we see all of this interesting structure in the dust emission. So these are images from the D-Sharp survey, which was a survey of a bunch of disks with ALMA at very high angular resolution. And you can see that many of these disks have ring and gap substructures. Some have spiral arms, some have azimuthal asymmetries, and we think that a lot of this substructure is related to ongoing planet formation in these sources. In addition to those observations of disk substructure, we have other more direct evidence of protoplanets forming in the disks. These are some sphere observations of HD 169142 done by our own Ian Hammond. So in these observations, you can see this blob is emission from a circumplanetary disk around the protoplanet, and this structure is the outer part of the spiral wake created by that protoplanet. We can also find evidence for embedded planets by looking at gas emission in disks. So these are ALMA observations of CO in a different disk, and if there's a protoplanet embedded in the disk, it will disrupt the flow of gas in the disk, causing deviations from Keplerian rotation that can be seen in this kink in the observations, which is reproduced in models that included a protoplanet embedded in the disk. So now we know that disks are very dynamic environments, and we know that the planet formation timescale has to be short in order for us to be seeing evidence of protoplanets in these disks. Protoplanetary disk lifetimes are only a few million years, so in astronomical terms that means you have a very short timescale to grow solid objects from the size of ISM dust, which is micron sized, all the way to planets. So given that we have evidence that planet formation occurs rapidly, we of course want to find ways to investigate the sizes of dust grains in those disks. This is important because dust grain sizes affect what the temperature structure of the disk is going to be, and therefore affect the disk chemistry. They also affect the degree of dust-gas coupling, and they affect how what planet-disk interactions are going to look like. For example, the dust grain sizes affect how dust grains are going to be affected by things like pressure maxima created by planets embedded in the disk. So since at this point a sample return mission to a protoplanetary disk isn't exactly practical, we have to learn about this dust by the radiation it emits. So I'm going to be talking about how we can use polarization observations to learn about dust grain properties. But the initial motivation for doing these kinds of polarization observations of disks was actually something completely different. It was to try and trace the magnetic field morphology in the disk. Because we think that the magnetic field is very much related to how protostars accrete mass from the disk. So you can use polarization observations to trace magnetic fields, because in the presence of a magnetic field, basically elongated spinning dust grains can become aligned with their short axes perpendicular to the magnetic field. Those elongated grains are going to preferentially emit radiation along their long axes. So you'll observe polarized emission where the direction of polarization is perpendicular to the magnetic field direction. These diagrams on the right show what you would expect to see in polarization if you have a toroidal field in a face-on or inclined protoplanetary disk. So these gray circles or lines represent the shape of those spinning elongated dust grains sort of projected along our line of sight. So you can imagine these kind of like washers strung along a wire. So in this face-on view of a disk, you're seeing mostly the edges of the washers. So you'll see polarization vectors arranged in this radial pattern. In an inclined disk, along the minor axis, you're going to see those washers edge on, so you'll observe polarized emission from them. But along the major axis, those spinning elongated dust grains are going to look more circular in projection from your point of view, so you'll observe less polarization along the major axis. So given how important we think the magnetic field is to star formation, once ALMA was up and running with its polarization capabilities, it got pointed at one of the biggest, brightest disks in the sky, HL Tau, to try and do these polarization observations to trace the magnetic field in the disk. And this has been done successfully in the ISM. For example, this is an all-sky map showing the direction of dust polarization tracing magnetic fields. However, when HL Tau was observed with this same technique, what was seen looked nothing like what we expected. So not only do we have a very different polarization morphology than what we would expect from dust grains aligning to a magnetic field, the polarization morphology actually changes between different wavelengths. So in these images, these contours represent Stokes' I, or the total intensity. The blue shading represents polarized intensity, and these red lines represent the direction of polarization, and they're scaled so that their length corresponds to the direction of polarization. So you can see that as we go from 3.1 millimeters to 870 microns, you transition from this kind of azimuthal arrangement of polarization vectors to a morphology where the direction of polarization is parallel to the disk's minor axis. So since these observations don't look like what we would expect from dust grains aligning to a magnetic field, a lot of work has been done to figure out what might actually be behind this type of disk polarization and what we can learn about the disk from it. So I'm going to start by talking about these observations at 870 microns that show this morphology with the direction of polarization along the minor axis. We think that this is most likely the result of scattering. So in this case, I'm talking about the scattering of thermal emission from dust grains by other dust grains. And this diagram shows how, as long as the scattering angle is non-zero, you're going to observe light that's at least partially polarized, and the polarization fraction is highest when the scattering angle is 90 degrees. And the interesting thing about this type of scattering is that the polarization fraction you observe is highly dependent on the maximum dust grain size. at least for compact spherical dust grains. So you can see in this plot that as the maximum dust grain size increases, the wavelength where this total polarization fraction peaks gets longer and longer. And disk geometry also affects what you're going to observe in scattering polarization. So like I said, the polarization fraction is highest when the scattering angle is 90 degrees. So you can imagine that, in a face-on disk, if you have most of the emission coming out from the center of the disk where the temperature is highest, if you have a photon that's coming out radially and hits a dust grain and scatters at 90 degrees, it'll be scattered into your line of sight, and you'll observe polarized emission arranged in this, with the direction of polarization in this azimuthal orientation. On the other hand, in the opposite extreme, where you have a very inclined disk, if you've got a photon coming out from the center of the disk along the major axis that gets scattered at 90 degrees, it's going to be scattered into your line of sight, and you'll observe the direction of polarization along the minor axis. On the other hand, if you've got a photon that's coming out along the disk's minor axis, a 90-degree scattering angle is going to be out of your line of sight, so you're not going to observe much polarized emission that's parallel to the disk's major axis. So in addition to HL tau, this polarization pattern that's consistent with scattering has been observed in a bunch more disks, especially at wavelengths of around 870 microns, which is ALMA band 7. So like I said, you can use these polarization observations to constrain the sizes of the dust grains in the disk. So the polarization fraction peaks when the maximum dust grain radius is of order the observing wavelength over 2 pi. So the fact that we're seeing polarization at these millimeter and submillimeter wavelengths implies a maximum grain radius of about 100 microns. But of course, that's not the only way that we have to measure dust grain sizes. More commonly, dust grain sizes are measured by looking at the spectral index of the dust emission. So you can't directly measure the dust opacity, but what you can measure is the spectral index of the dust emission. You can relate that to the index of the dust opacity, and then relate that to the dust grain sizes. And these SED observations imply a dust grain size of about 1 millimeter in the same disks where polarization observations imply dust grain sizes of about 100 microns. So some possible reasons for that discrepancy include, maybe instead of being compact spheres, the dust is irregular, or it's a porous aggregate. Those are both going to affect how dust grains will scatter light, and they complicate the way that polarization fraction is related to maximum dust grain size. Also, we know that disks aren't uniform. Many of them have rings and gaps. So if you have optically thick substructures like dust rings, that can also affect both the size estimates that you get from scattering and the size estimates that you would derive from SED observations. So in addition to the type of polarization we observed at 870 microns, we see this very different polarization pattern in some disks at longer wavelengths, like 3 millimeters with ALMA, where the polarization vectors are kind of arranged azimuthally, and you have this ring of polarized emission. So a lot of the work that's been done to model that azimuthal polarization pattern has been considering some kind of way of aligning elongated dust grains that then emit polarized emission. So two forms of grain alignment that have been looked into are radiative and aerodynamic alignment. In the case of radiative alignment, it's kind of a similar mechanism to the alignment of dust grains to a magnetic field, except instead of the magnetic field, dust grains are aligning to the radiation anisotropy in the disk. In the case of aerodynamic alignment, you've got elongated dust grains that are experiencing a headwind from the gas because the dust is orbiting at Keplerian velocities, whereas the gas, which has pressure support, is orbiting at sub-Keplerian velocities. However, neither of these mechanisms by themselves reproduce what we see in polarization at 3 millimeters. They both predict more azimuthal variation in the polarization fraction than what we actually see in observations. So because of the sort of projected shapes of these elongated dust grains that you would see along your line of sight, in the case of radiative alignment, you would end up with very little polarization along the minor axis. And in the case of aerodynamic alignment, you would end up with low polarization fractions along the major axis. So since we observed, that change in polarization morphology with wavelength and HL tau, one of the first questions that we wanted to ask was, does that pattern hold for all disks? So it turns out the answer is no. So this is data from a survey that I did of polarization at multiple wavelengths in a few disks in the torus molecular cloud. So in these images, the black contours represent Stokes I at 870 microns. The red vectors represent the direction of polarization at 870 microns, and the blue vectors represent the direction of polarization at 3 millimeters. So you can see that in HARO 613 and V892 tau, we've got a similar transition of polarization patterns to what we saw in HL tau at those wavelengths, where you go from this azimuthal arrangement of polarization vectors at 3 millimeters to having most of the polarization vectors parallel to the disk's minor axis at 870 microns. Whereas RY tau and MWC 480 are more consistent with scattering at both wavelengths. So one of my collaborators from grad school has done some work on modeling what might be creating this transition of polarization morphologies that we see in HL tau as we go from 3 millimeters to 870 microns. So you can create this type of transition of polarization morphologies if you have polarization from both scattering and from aligned elongated grains. So at low optical depths, at long wavelengths, there's very little scattering to begin with, so you mostly see polarization from aligned grains. As you go to higher optical depths, you get more scattering, but you also get dichroic extinction of the polarization from aligned grains, so you mostly see this scattering polarization. So this still relies on there being two mechanisms creating polarization in this disk that just dominate at different wavelengths. So one of the things that I'm working on is seeing if we can explain this entire polarization spectrum with just scattering alone. So in contrast to disks like HL tau, in RY tau and MWC 480, we see scattering at two widely separated wavelengths. This is something that we didn't expect based on earlier models of polarization from scattering that had assumed that you have, compact spherical grains, that you have single scattering, and that the dust grain distribution is described by a power law with one defined maximum dust grain size. We've done some modeling to take into account different things that could affect the outcome of scattering polarization, and that could maybe lead to us observing polarization from scattering at these two widely separated wavelengths. So the outcome of what you're going to see in a disk from scattering polarization is affected by optical depth. And that's because optical depth affects what a grain sees, what its incoming radiation environment is. So you can imagine that if you had a dust grain embedded in a very optically thick environment, it's going to see a mostly isotropic radiation field coming in towards it. It's going to scatter light isotropically, and you're going to observe very little net polarization from scattering. On the other hand, if you've got a dust grain embedded in an anisotropic radiation environment where most of the photons coming towards it are coming from a particular direction, it's going to scatter light more in some directions than others, and you'll observe scattering polarization. So this plot shows how the polarization fraction depends on the optical depth, and at very low optical depths you're not going to get much scattering at all, so the polarization fraction is low. The polarization fraction then peaks at around tau equals 1, and then decreases and asymptotes off to a lower value as the radiation environment the dust grain sees becomes more isotropic. So in our scattering models, we've considered a few different dust grain populations. To test the effects of optical depth, we've created these single population models where there's one defined maximum dust grain size, and then the rest of the grains follow a power law distribution of sizes. And we've run models with a few different maximum dust grain sizes and either high or low characteristic optical depths. And then we've also done some work on testing what effects dust grain settling would have on the outcome of scattering. So in this two population model, we've got a population of larger dust grains near the disk's midplane, and populations of smaller dust grains above and below the midplane. So these images are showing the polarization fraction versus distance from the disk center along the major and minor axes of RY tau and MWC 480. So the features that we're trying to reproduce in our models are the fact that we have an observable degree of polarization at both wavelengths, and we've actually got a higher polarization fraction at band 3 in the centers of the disks. So these are some images that were created using the single population models. So with this modeling and with these observations, we're not able to pin down an exact definitive dust grain population because basically we're missing information from the intermediate wavelengths between 3 millimeters and 870 microns, but we can rule out some dust populations. For example, if you had a power law distribution of dust grains with a maximum dust grain radius of 490 microns, you would produce an observable degree of polarization at 3 millimeters, but very little polarization at 870 microns, which is not consistent with what we see in the data. But if you look at a dust grain population with a maximum grain radius of 200 microns and a high characteristic optical depth, you can reproduce the fact that there is an observable degree of polarization at both wavelengths, and the fact that the polarization fraction is higher at 3 millimeters than at 870 microns. And these models have not been, fine-tuned to match what we see in the data, but we wanted to have kind of a proof of concept showing that things like optical depth and size-dependent dust grain settling would affect what you saw in scattering polarization. Our other class of models was the two-population model that includes vertical dust settling, so you've got larger grains near the midplane, smaller grains above and below. And for MWC 480, you can reproduce the higher polarization fraction at band 3 in the center of the disk with this type of model. However, the type of dust grain population that we've set up here is not necessarily a realistic thing to physically have in the disk. Yes, so these are plots showing the dust grain models where we did manage to reproduce the fact that we've got a higher polarization fraction at band 3 in the center of the disk, and we've got an observable degree of polarization at both of the wavelengths that these disks were observed at. So now I want to go back to some of the possible sources or resolutions to that discrepancy between dust grain size estimates from scattering and those from SEDs. So like I said earlier, disk substructure is something that can affect the dust grain size estimates that you get from both of those techniques. So this is showing some models of HD 1632-96, where in these models the disk has optically thick rings and optically thin gaps. So you can see that in this model you've got higher polarization fractions in the gaps of the disk, but when you basically, if you sort of smear out this polarization pattern by convolving it with a beam, that affects what you actually would see in the polarization observations. So this is showing polarization fraction versus disk radius, where this black dashed line is the unconvolved model, and the red line is the model convolved with the beam. So you can see that convolving with a beam basically smooths out these fluctuations in polarization fraction that are correlated with the ring and gap substructures. Another way that disk substructure could affect scattering would be if you've got different dust grain sizes in the rings versus in the gaps. So in this model, you've got 140 micron dust grains in the rings and larger dust grains in, other way around, small 140 micron dust grains in the gaps and larger dust grains in the rings. And again, this is a model of that same source, HD 163296. So this is modeling the scattering polarization at 870 microns. So those 140 micron dust grains in the gaps are going to produce an observable degree of polarization at 870 microns, whereas the polarization fraction is going to be lower in the rings if you've got larger dust grains there. So a lot of the sources that I've shown before, in fact, really all of them, were taken at a low enough resolution that we didn't resolve the ring and gap substructure in the disk. However, we've now got some polarization observations of HD 97048. So these images show Stokes I and percent polarization with the directions of polarization plotted on top of them. So you can see that in the gaps of the disk, we have a higher polarization fraction than in the rings of the disk. And that's something that was predicted both by models that have different optical depths in the rings versus the gaps, and models that have different dust grain sizes in the rings versus the gaps. We can also see that the direction of polarization is correlated with disk substructure. So this histogram shows the polarization angles for the inner cavity, first ring, and first gap. So you can see that in the ring, the polarization angles are more aligned with the disk's minor axis, whereas there's more variation in polarization angle in the cavity and the gap. And that has to do with sort of where the radiation is coming in from in the rings versus the gaps. In the gaps, you're going to be mostly seeing radiation coming in from the adjacent rings. So if that radiation is coming in from the adjacent rings and gets scattered at a 90-degree angle, you're going to see polarization that's more azimuthally aligned in the rings, or in the gaps, sorry. So at this point, we're still kind of searching for that grand unified theory of dust polarization that can explain both the polarization spectrum and the spectral energy distribution with one dust population. So as I mentioned before, one possible way of resolving this might be by looking at scattering from irregular grains. So these are experimental measurements of polarization versus scattering angle that were taken in a lab by basically looking at some samples of crunched up rocks. If you take those lab measurements of polarization fraction versus scattering angle and model the polarization in HL tau using them, you can create polarization that's aligned with the disk's minor axis, even if you have like millimeter-sized grains, as long as the grains are irregular. Whereas if you had grains that were that big, that were spherical, if you use Mie theory to calculate what the resulting polarization would be, you'd see something that was basically 90 degrees flipped from what we see in the polarization observations. And we can also investigate how dust grain porosity would affect scattering polarization. So this plot on the right is showing the degree of polarization times the effective albedo versus observing wavelength for dust grains with different maximum radii and also different filling factors. So this considers filling factors of 1, which is a solid sphere, and 0.1, which is a compact dust aggregate. So you can see that for a compact sphere versus for a solid sphere versus a compact aggregate of the same size, you get different polarization spectra. And we think that for some sources investigating scattering from porous dust grains is a promising direction to go in, because, for example, in these observations of HD 97048, Christoph in his 2019 paper showed that if you've got compact dust grains of a certain size, they'll create rings that are much thinner than what you actually see in the ALMA observations. Whereas if you take dust grains the same size, but make them fluffy, so they've got a lower Stokes number, you get wider rings that are more consistent with what we actually see in the ALMA observations. So future research into disk polarization is going to involve a combination of more detailed observations and more detailed modeling. So in terms of the observational branch, we want to observe more protoplanetary disks at more wavelengths and at higher angular resolutions and sensitivities. And on the modeling side, we want to incorporate irregular and porous dust grains into our models, calculate how they would scatter light, and then put those calculations back into something like MC FOST to model the expected polarized emission from those disks. And both of these in combination, I think, are going to go a long way towards nailing down how big the dust grains in these planet-forming disks actually are, which is really important for all kinds of studies into planet formation. Yeah, so.
Questions?
Does dust composition affect the scattering and the polarization?
Yes, it does. So a lot of these models are looking at sort of the silicate dust grain mixture that that's been used in like the D-sharp papers. But yes, the dust grain composition would affect what you would get in terms of scattering polarization, as does whether the dust has an ice mantle and what the ice mantle is made of.
Can I ask about dust grain size? You know, you mentioned the gases moving at subcapillary speeds because of the pressure gradient. But what's the transition between its size of dust for it to be dragged along by the gas and not? You said the grains were going on capillary.
Right. So once the dust gets large enough, it is going to be less coupled to the gas. I don't remember off the top of my head what types of dust grain sizes that would be, but I know that once we're talking about like millimeter-sized dust grains, those are usually considered to be pretty decoupled from the gas.
I was just curious about all of your model predictions for your polarization as a function of radius, I guess. I mean, they all have this like strong variation in them. So like your red curve is like double bumped, and then you've got this strong peak in the other curves. So is that something you understand? Because your observations by contrast seem very steady or just slowly varying over the disk there.
Right, that's basically an optical depth effect. So at the shorter wavelengths, the disk is going to get pretty optically thick near the center, which is going to attenuate the polarization fraction. And then as you go out to really large radii, the dust density decreases, so you're getting less scattering to start with.
So what does it mean then in your bottom right, the fact that you don't see this attenuation in, say, the red points, like the one below that? Yeah.
This one?
So like the red points just show a linear increase. Well, it's not even it. It's weird, right? Because it's right across the center of the disk.
Right. So this is for MWC 480, where we don't have the best signal to noise, and also the polarized region is not much bigger than the beam size.
So it's just smoothed by the beam.
So beam smoothing and the low signal to noise might be affecting what we're seeing in MWC 480. So I think that getting higher resolution observations would help us to see if we are seeing this this dip in polarization at the center of the disk.
So I assume then that means that your red lines are not being smoothed by the beam for the prediction, so that's the sort of unsmooth prediction?
Yeah, these have actually, so the models actually have been convolved with a beam, but they're not fine-tuned to reproduce the exact polarization fractions that we're seeing in the data. So if you tuned the grain size and the and/or optical depth, I think you could match these polarization fractions more exactly. The reason we didn't do that, at least in this paper, is that there's a degeneracy between the effects of optical depth and dust grain size. So basically, you can turn either knob and get the same results, at least within the constraints of these data.
So on the same plot, so you have this, well, I'm not sure how well the data is, how good the data is, but the red dots seem to have this linear increase from left to right. And that is just like the left-right of the disk, right?
Right.
I was wondering why even your model has left-right asymmetry.
Right. So that has to do with sort of disk geometry and the relationship between scattering angles and the angle to your line of sight. So basically in an inclined disk, you would expect to get a higher polarization fraction from scattering on the near side of the disk than from the far side, at least as long as the dust grain layer is not completely geometrically thin.
So, sorry, so this is near to far?
Right, this is the near side of the disk, this is the far side of the disk.
Oh, okay.
So in your images, pictures, you always speak that the gas is something prolate. Is there any reason the dust couldn't be, say, oblate? And how would you know the difference? And the second question I have is also about, can the dust spin?
Yes, so the dust, the dust can spin, and as far as prolate versus oblate dust grains, so I'll be honest, I always get the definitions mixed up, but right. But I think that the radiative and aerodynamic alignment, one of them is considering grains that would basically be oblate, one of them is considering grains that would basically be prolate, at least in terms of the projected grain shape that you're going to see.
Probably missed very early on, but can you explain again why the scattered light is preferentially on like 90 degrees?
Right. So when I'm talking about the 90-degree scattering is, the dust grain can scatter light in any direction. It's just that the polarization fraction is maximized when the scattering angle is 90. So most of the polarized emission that you're seeing is coming from light that has been scattered off of a dust grain at a 90-degree angle. That's just where the major contribution to the observed polarization is coming from.
Is that because of the shape of the dust grain? We also had 90 degrees in the spherical dust.
So this...
What is the polarization like around?
Right, so this is just when we're considering Rayleigh scattering. So the reason the dust direction of polarization is mostly along the parallel to the minor axis, I think is best illustrated if you think about the extreme case of a disk that's basically edge-on. So imagine you've got an edge-on disk, you have a photon that's coming out from the center of the disk, hits a dust grain, and let's say this photon is coming out along the disk's major axis, it hits a dust grain, and then if it's scattered at a 90-degree angle, that 100% polarized light is scattered into your line of sight. If you've got a photon that's coming out along the disk's minor axis, from your point of view, it hits a dust grain, it gets scattered at a 90-degree angle. That scattered photon is not going along your line of sight.
Sorry, I was more wondering about this, why the scattered light is polarized per grain.
Yeah, I mean, it's just because we're considering basically Rayleigh scattering here, so the light is 100% polarized if it's scattered at a 90-degree angle.